Well, this is the title of my talk is the Escherization of David Smith's Spectre, and it also will contain various other things. In particular, one thing which I didn't even realize before, after I'd given the title to the talk. We'll come to that shortly. Now, what I mean by an Escherization is illustrated well by this picture here. This is from the work of N.C. Escher, and it is a nice representation of a particular tiling of the plane where the tiles are distorted from being just simple parallelograms or something like that to these wonderful shapes. And Escher was a real master of doing this kind of thing. It's rather a shame that he did not live long enough, or we were too slow, I guess, for him to be acquainted with non-periodic tilings, because they weren't around before that. Okay, let me move on. I'm going to show some pictures from an article I wrote for this particular book, which was The Artful Eye, by the various people you can see there as editors. And I was leafing through this book to find an Escherization that I had used. It also revealed something else, which I wasn't expecting. I'll come to that later. Now, this is my kite dart tiling, just a straight tiling, you can see. I think the darts are done slightly grayer than the kites, never mind. Now, what you can do is replace the darts and the kites. At the bottom, you see I have little spikes to force the only matching you can do is legal matching. And if you get the little spikes to fit where the slots that they fit in, then it forces you to produce the proper tiling, non-periodic tiling. Now, you can do something more interesting, which is the two at the top, which is what I'm calling Escherization. You can Escherize the kite shape to produce the one on the left, and the dart shape to produce the one on the right. And this shows you the sort of pattern you get. This is, I rather like this one, but more like Escher in a certain sense is one made by Richard Hassel, which is the same kite dart tiling, I think, but with these frogs. And you see their legs are doing interesting things, which is the sort of thing that Escher liked to do. Anyway, that's an example. So there are various different Escherizations of the tilings that I had. I want to move on to something else. This is the Spectre tile, and you can clearly modify the edges in various ways, as I indicated here. This is, I think, from the paper, the famous paper, which contains these Escherizations. Well, I mean, they are Escherizations, but they're not meant to be creatures of recognizable. They're just showing that you can force the tiles either to have reflections or not to have reflections. Well, the reflections don't. Yes, you can have it periodic if you. Well, some of you. Well, let's not go into it because this is in the paper. It's not what I want to discuss. It's just showing what the Spectre tile is and how you can modify it in a way which allows the tiling to remain and maybe remain non-periodic. Now, this is the example that I have here. I may say that I only finished drawing this particular picture earlier today. It was only shortly before this talk was to be given. I have another one, and I wanted to use a slightly different one, which it's rather roughly drawn, so that the tiling, I think it needs a bit of improving the shapes to make it exactly right. But I should give you an idea why this is a tiling, an Escherization of the Spectre tiling. It is the Spectre, but you modify the various. You see, when I first heard about the hat, I thought this is exciting, and I wondered whether you could Escherize that. But the trouble with the hat is that when you turn it upside down, I mean, you need to have it right way up and mirror reflected to make the whole tiling. And you have to match the edges with the mirror reflection and in all sorts of different ways. And to make all these criteria satisfied, you can't modify the edge from a straight line. So there's no way you can Escherize, in this sense, the hat tiling. However, the Spectre has the advantage that, first of all, you don't turn it over, so you don't have to worry about, I mean, you don't have a reflection, if you like, of the tiling. So you don't have to worry about making it match one way or the other. Moreover, it's consistent with having one, I mean, you have the freedom of taking the single edge and doing something with it. And as long as you do every other edge inconsistently with that particular edge, either positively or negatively, then you can make an Escherization. But the trick is to make that Escherization look like something like a bird or a creature of some sort. So this was my attempt at making a nice little bird. It's also, if you notice, it's got claws on its wings. I'm told that there do exist. I think in prehistoric times there were lots of them, but there is such a bird which is called a Hoatzin. So I'm going to call this a Hoatzin, this bird, which does have, at least the juveniles do have claws on their wings in just the right spots. So that's what I'm calling this here. Anyway, you can see that the claw shapes fit together into its beak, and that was sort of the driving force behind this shape. It's not the way up that you normally think of this. This doesn't look the way up to make it look like a spectre or something. It's the way up to make it look like a bird. And I was taking advantage of that. I haven't got very far in making a tiling of this, but I'll indicate the sort of thing you can do. You fit the beaks together in this way. I think I should have done a more interesting one with one at the top there, but never mind. You get the idea. And with a little bit of honing and improving the shapes a little bit, I think they're a little bit too hastily done at the moment. This would give you a genuine Escherization. So that's the title of the talk. And but when I was looking at these pictures in my article in the Shepard, well, the Grimham with Shepard and various other people. No, I don't think that Shepard is one of the authors, but it's Richard Gregory is one of them, and there's several people who wrote articles for this, and I wrote one. They're not on tilings, most of them. They're on other things, but I wanted to say something about tilings. Now, in that article that I wrote, you also find this picture here. And I'd seen this lots of times. It's a 12-fold quasisymmetric tiling. You see, when I say 12-fold quasisymmetric, my one's a 5-fold quasisymmetric. That is, if you make a very, very big version of the tiling, the bigger you make it, the closer you can make it to have that symmetry. You can't have 5-fold symmetry and have a translational symmetry. That's contradictory. But you can have 5-fold, so almost 5-fold symmetry, to the extent almost meaning that the bigger the shape is, the more closely you can match to 5-fold symmetry, and likewise to a translational symmetry. Now, this is an example originally based on Joshua Sokolar, and I think Nissen. This is the version that Nissen had of Joshua Sokolar's 12-fold tiling. So you have, by looking around the outside edge, you can see that it sort of has a very close to a 12-fold symmetry. In the middle, you can see it can't be exactly 12-fold symmetry, but it has this quasi 12-fold symmetric nature. Now, what struck me about this thing is if you look carefully at the tiles, you can fit them together, and I've done it here, to make spectres. This is very remarkable. I hadn't expected that at all. I've taken a large region. You can't, of course, tile with the spectres. Well, first of all, because the ratio of the little, you see there's a 3-fold tile and a 2-fold tile, 3-fold symmetric tile and a 2-fold symmetric tile, and you have to take one of each to make a spectre. And that's what I indicated here. But since the 12-fold tiling, you need rather more of the 2-fold symmetric ones, you've got them left over. So it certainly isn't a tiling of spectres. It's quite striking that you get this spectre playing this other role completely different. And had no idea that it would do this. You see I don't know if you can see, maybe the green ones are easier to see through. You can see that they are made out of perhaps I can go back on this. You have the two shapes, the two-fold symmetric shapes and the three-fold symmetric shapes. And you take one of each and it makes a spectre. And so I've done that sort of rather non-systematically over the whole picture, but I've done it in such a way so that they do make actual spectres. Curiously enough, you can also make these Buddhas, which this is there's nothing special about the Buddhas, they're all over the place. But I just indicated since the Buddhas seem to feature very much in the actual tiling of the David Smith shape. And I just was struck that you have these Buddhas also, they're all over the place as well. Anyway, I think that's all I wanted to say. And so thank you very much.
So Roger Penrose, everybody, who we now owe $8. So I think, have we still got, is Roger still on there?
Yes, thank you very much for joining us, Roger, and warm welcome from the large G4G audience here. I'm sure everybody was delighted with that.
Thank you. Are there questions or not? I don't know.
We do have some time for a few questions. Does anyone have a question?
So I'm going to repeat the question. The question was, what was the reason why the hat tile, the original aperiodic monotile, wasn't suitable for Escherization?
Oh, no, the hat, I maybe said it rather too quickly. The hat doesn't work because you need it reflected as well. And that means that the edge, well, there are two reasons. One is you need it reflected. And secondly, that all the different edges, if you chase it around in the tiling, will match every other one. So you've got to match edge to edge and reflected edge to edge. And there's no way of doing that unless it's a straight line. See, if it's got to be reflected, the only way you could make it, I'm talking about jigsaw tilings, you could color it, that's a different question. But to Escherize, I'm thinking of jigsaws. So if it goes out in one thing, it's got to match going in on the other side. And if it matches reflecting, then if it goes out on one side and in on the same side, it's got to be flat, straight. So that's the trouble. You can't get anywhere with Escherizing the hat, unfortunately. I tried, but then I realized it was a hopeless task. But I was very pleased for all sorts of reasons. But when I saw the Spectre, that it does it's only one way up, which is a good thing. And the edges are only of one type, either positive or negative, depends on which way around. And so you can do any shape you like, and its negative has to appear as well as its positive, and you just want to try and make that shape look like something. So you've got a lot more freedom to do something with it. It'll be interesting to see other examples of Escherizations. I'd like to see that.
Okay, thank you. Is there any connection between the Spectre tile and Islamic tilings, like Alhambra tilings, for example?
I doubt it very much. I mean, when I produced the, well, I had a 6 tiling of the plane, which involved 6 different shapes, and then I got it down to 2. And I remember I got it down to 4, and I was quite pleased with that. And then when I got it down to 2, I thought, this is ridiculous. It's much too easy. Surely it's to be found in the Islamic tilings and things like that. And some people claim to see it in Islamic tilings, but it's not there. I don't see that. They were too interested in making it periodic deliberately. So the idea, I think, would have horrified them in some way. I don't know. But there is no example of any aperiodic set, as far as I'm aware, in the Islamic tilings. So certainly not the Spectre. There's no hope for that.
Would Penrose mind talking about their relationship with Martin Gardner?
Oh, I see. Well, he was a lovely man. I had a great time. I used to visit him from time to time. And I remember when Stephen Hawking produced his book, A Brief History of Time, he had got Carl Sagan. In order to get it popularized in a way, he got Carl Sagan to write a foreword. And I thought, oh, that's a good idea. Maybe I can get for my book, which was sort of being written at the same time, although it was much longer. So it didn't come out until a long time after Stephen's book. And I thought, who can I get to write a preface or an introduction or something like that? And so I wrote to Martin Gardner rather nervously because he might not approve of the point of view I was taking. And he said, no, I agree with you. I'm very glad to write one. So he was very helpful to me, and I'm sure he helped people to buy the book. So that was a good thing, as far as I was concerned. No, but I met him on several occasions, got on with him very well, and I visited him in his home several times, I think. At least twice, I'm not sure how many times, but and I'd met him at conferences occasionally too.
Okay, thank you very much. We're now out of time, but we all very much appreciate your joining us today.
Perhaps I could mention one thing that I forgot to say, is that it's curious, I find, that this 12-fold quasi-symmetric pattern has so much connection with the Spectre tile. I mean, you find not only the Spectre, but you find the Buddha, the way it fits together as the central part of the way that the tiling is constructed. Yet it's not 12-fold quasi-symmetric. You can see that certainly I think the Buddhas are always at 60 degrees or 120 degrees or parallel to each other, whereas in the ones I showed, you see some of them are 30 degrees from each other. So it's a different tiling. Whether there is more of a connection, I would be very interested in this, because there's no attempt to make it 12-fold quasi-symmetric. Yet it seems to have all these connections, quite unexpected. I mean, I was not expecting to see in that circular Nissen tiling any connection with, and then I looked at it, and my God, it's made out of these two shapes. I haven't even seen that in the Spectre discussion. If you could take each Spectre and divide it into two shapes, and these are the two shapes which are shown in the tiling which I just showed in this talk. One of them is 3-fold symmetric, and the other is a 2-fold symmetric. And you fit them together in this asymmetrical way, and it produces the Spectre. So it strikes me that there ought to be some connection with those 12-fold quasi-symmetric tilings, which is not really brought out in the discussion of, at least not what I've seen anyway. You see 3-fold connection with 3-fold symmetry, or 6-fold. And also there's another feature which I find interesting, because the hat tiling is based on a lattice. You have this lattice, which is the triangular lattice, and the hexagonal lattice superimposed each other, and you get these quadrilateral shapes. And the hat is built out of those quadrilateral shapes. So you have certain tilings which are built out of a basic, which is a periodic tiling, and others which are not. And some of the Aman tilings you can base. I had a version of it. I had meant to show it in my talk, but I forgot about it. There's one based on a square lattice. So you can certainly make that based on a periodic tiling, an ordinary lattice. But the ones which have 5-fold symmetry, you certainly can't. And see, if you've got 4-fold symmetry, then there's a chance. But if it's got a different, which is a non-crystallographic tiling, there's no lattice underneath. But when you go to this, from the hat to the Spectre, then it's, rather than having a basic lattice pattern, it doesn't have one. So it shares with my tilings and some of the others, the fact that it doesn't have a base lattice. So that's intriguing.
Okay.
I say this is a wonderful new opening into tilings, which was completely unanticipated. I had toyed a little with Einstein tiling, but not got very far with it. With a different idea, it might be useful to think about that idea, that you could make a tiling which is sort of hierarchical, but it tilts as an irrational angle, so that it could never be periodic because it has a tilting. You can have tilings like that, but to force such tilings, I didn't know how to think that. That's just another curious feature.
Okay, well, thank you for all of those additional thoughts. And we're going to have to say goodbye, but we all very much appreciate you joining us. Thank you.